Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are going to talk about causal inference. This topic is based on a tech blog with the title How to Determine Causal Effects When A-B Testings Are Infeasible Through Adoptor Analysis, written by the data science team from Walmart. You can find the blog link in this episode's description. Throughout this episode, we will dissect this topic from both business and data science angles. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Walmart is one of the largest retail giants in the world. It operates an extensive network of stores and has a rapidly growing online presence. To maintain its competitive edge and ensure customer satisfaction, the company leverages data to make quantitative decisions across all areas. These decisions range from inventory management to pricing strategy to marketing campaigns and product changes to improve customer experience. Understanding the causal effects of these decisions is crucial. For instance, if Walmart introduces a new loyalty program, it's essential to know whether the program itself drives increased customer spending or if other factors are at play. Accurate causal effect analysis helps Walmart to allocate resources efficiently, optimize their strategies, and ultimately improve the business performance. Causal inference is the process of determining the causal effect, meaning whether a cause and effect relationship exists between a treatment and an outcome. The treatment could be a new marketing strategy, and the outcome could be increased sales. Well, the standard A-B testing framework is a robust method for establishing causality by randomly assigning participants to control and treatment groups. It isn't always feasible. For example, assume an e-commerce subscription business want to determine whether changes in member benefits would result in increased spending or retention. In this situation, conducting an A-B test can be difficult because it is impractical to randomly assign some members to receive the new benefits while withholding them from others. Additionally, operational constraints, ethical considerations, and resource limitations can make A-B testing infeasible. In these cases, causal inference methods like difference in difference, regression discontinuity, and synthetic controls can become essential. These quasi-experimentation techniques allow businesses to estimate causal effects even when randomized experiments are impractical. They provide a way to infer causality from observational data, helping businesses like Walmart to make informed decisions in complex real-world scenarios. Despite their utility, standard quasi-experimentation techniques can come with quite big challenges. One major issue is the presence of confounding variables. Those confounding variables are factors that influence both the treatment and the outcome, potentially skewing the results. For instance, when Walmart introduces a new customer benefits, variables such as customer tenure, engagement level, pricing changes, and concurrent promotions can all affect the measured outcomes like spending or retention. These confounders make it difficult to isolate the true effect of the treatment. Overcoming these challenges is crucial for deriving meaningful insights and make reliable data-driven decisions in a dynamic business environment. Now that we've understood the business problem to solve, let's dive into the data science side to see what solution the team proposed. To address the limitations of traditional quasi-experiment techniques, the data science team at Walmart proposed a framework called Adoptor analysis. This framework comprises three key techniques and operational steps: defining an adopter, leveraging propensity score matching, and conducting a difference-in-difference calculation. Let's examine each step closely. The first step is to define an adopter. An adopter is a user who has utilized the benefit at least once. For certain benefits, such as an item price discount that can be redeemed in the next purchase, we may consider 2 purchase cycles as the adopter threshold. Since there is no randomization to pre-select users into control and treatment groups, defining an adopter helps the team to create these groups. The treatment group is created to comprise those adopters, and the control group comprises non-adopters. This is the foundation for conducting causal analysis to understand the treatment effect. Step 2 is to apply propensity score matching. Given that causal effects can't be measured through A/B testing, defining an adopter means the causal effect will be calculated from an observational study where participants are not randomly selected. In these observational studies, selection bias often occurs. For example, if we want to measure the effect of a new benefit, users who are more engaged with the platform might naturally be more likely to adopt the benefit. Thus, evaluating the incremental engagement contribution from this new benefit may naturally be higher for those adopters. This is an example of selection bias. Propensity score matching aims to minimize selection bias by creating comparison groups with similar observed characteristics. This technique involves selecting a control group with characteristics similar to the treatment group and compare their outcomes. Propensity score matching is based on the probability of treatment assignment, giving observed baseline covariance such as demographics, prior engagement with the platform, tenure, etc. By doing this, we can create comparable treatment and control groups. In the subscription benefit example, the team calculates the propensity of a member to be exposed to a subscription benefits in the pre-treatment period. They then match members from the treatment and control groups based on their propensity scores within a specific threshold. The team can evaluate the matches by examining the propensity score plot before matching and comparing the means of the original and matched data to ensure the data is balanced across the identified covariance. Step 3 is to conduct a difference-in-difference calculation. Once we have matched the treatment and control groups on observed characteristics, the team can use the difference-in-difference technique to estimate the causal impact. Difference-in-difference compares changes in outcomes over time between a treatment group and a control group, isolating the effect of the intervention. Let's provide a simplified example of the price discount benefits to illustrate the concept of difference in difference. In this example, let's say there is a control group and treatment group. First, we observe and record the spending behavior of both the control group and treatment group before the price discount benefit is introduced. This gives a baseline of how both groups behave without the intervention. The treatment group's average weekly spending is, let's say, $200, while the control group's average weekly spending is $150. After introducing the price discount benefit, we observe the spending behavior for both groups over a defined post-treatment period. The treatment group's average weekly spending, let's say, is $250 now, while the control group's average weekly spending is $160. Next, we calculate the difference in spending for both groups from the pre-treatment to the post-treatment period. For the treatment group, the increase is $50 from originally $200 to $250. And for the control group, the increase is $10 from originally $150 to $160. We then can calculate the difference between the treatment and the control group's change in spending to isolate the effect of the price discount benefit. The final calculation is $50 minus $10, which is the treatment group's increase minus the control group's increase, resulting in a $40 increase. By conducting this difference in difference analysis, we can determine that the price discount benefit would lead to a $40 increase in average weekly spending for the treatment group compared to the control group. Using a propensity score matching before applying difference in difference method ensures the assumption that the treatment and the control groups follow the same trend in the pre-treatment period is met. This approach allows us to compare changes in customer spendings and retention over time and provide a clear understanding of the intervention's causal impact. Now we discussed both the business problem and technical solution. Let's wrap it up. In this episode, we introduced the concept of causal inference. We discussed how the data science team from Walmart determine causal effects when A/B tests are infeasible through adopter analysis. There are 3 steps involved. Define an adopter, apply propensity score matching technique, and then conduct the difference in difference calculation. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.